Okay, so our first unit on stoichiometry starts with a simple definition. You want to write this stuff down. Don't write what's in red. That's just to kind of talk about for now. But once you've paused and written everything down, then you can obviously play and we'll discuss it. So stoichiometry, basically, we're just using a balanced equation like the one that you see down below works like a recipe to determine how much reactant you need to make a certain amount of product. So if our goal in this case is to take water and break it down into hydrogen and oxygen, maybe we need that hydrogen for some purpose, like fueling a hydrogen fuel cell car or something like that. So we need to make a specific amount of it, and we need to know how much water is going to be required to make that amount. So that is what stoichiometry is in general. Here's an example question. Again, you don't have to write it down right now. We're going to answer this question later, but we're going to come back to it. I just wanted you to see an example of what a bigger, slightly longer stoichiometry problem is going to look like, and then we'll break it down into smaller bits. So an example of a longer problem would be, how many grams of water would you need to decompose to produce 45.0 grams of oxygen gas? So it's just saying, how many grams of this do we need to produce our goal, which in this case happens to be 45 grams of hydrogen. We're also going to produce some oxygen, but apparently in this question or in this problem, we're not worried about how much oxygen we're making. That's okay. So how do we do the math? Well, the first thing we have to recognize is that the equation is a recipe. It gives us a ratio. It tells us that 2 water molecules will break down to produce 2 hydrogen molecules in 1 oxygen molecule. But what does that have to do with grams? Well, we don't really know how many grams 2 water molecules would weigh, or how many grams 2 hydrogens or 1 oxygen, but we do know how many grams a mole of them weighs. So we can use the periodic table to help us out with this. So we also know that because moles are just molecules multiplied by 6.02 times 10 to the 23rd, we also know that if I have 2 molecules of water for every 2 molecules of hydrogen and 1 molecule of oxygen, those would also be mole ratios. So 2 moles of water would break down to produce 2 moles of hydrogen and 1 mole of oxygen. And that becomes important. Let's take a look at an example. How many moles of water would you need to produce 4 moles of oxygen? So I'm going to do this using dimensional analysis. So if you remember how that works, I just start with my number with units. So 4.0 moles of oxygen over 1. So moles of O2, and then I'm looking for moles of water. And the thing you have to understand is, in any stoichiometry problem where we're being asked to convert between 2 units, we can always go from moles of one substance in a balanced equation to moles of another. Because, if I go back to my balanced equation for a second, I have a molar ratio. I have, in this case, we're concerned with moles of water and moles of oxygen. And in the balanced equation, it shows me 2 moles of water for every 1 mole of oxygen. So that becomes the ratio that I'm going to use. And at this point, you might want to recopy that equation. I'll go ahead and just recopy it right down here. So 2H2O turns into 2H2 plus O2. I'm not really going to worry about the physical states, even though I do have them written up above. But I'm going to take my ratio, moles of water is 2, and moles of oxygen is 1. And I'm going to bring that down into my dimensional analysis, into my unit conversion. Moles of oxygen would then cancel, and so essentially it's just 4 times 2. So with sig figs, it's going to give me 8.0 moles of water. And does that make sense? Would I need twice as many moles of water as I'm producing moles of oxygen? Yeah, because there's a 1 in front of oxygen, there's a 2 in front of water. So let's go ahead and move on to another problem. what if we're trying to produce 45 grams of oxygen? All right, so this is a little bit more complicated. I'm starting with grams this time. And so I know I need to get rid of grams of oxygen. Now I want moles of H2O. So I'd like to put that on the top. The problem is there's no relationship between grams of oxygen and moles of water. It doesn't make sense to say there are this many, grams of oxygen, grams of O2, I should say, per this many moles of water. Elemental oxygen and molecular water are two different things. So we have to convert from grams of oxygen to something that we can then convert to moles of water. So if you think about it, well, it makes sense. We've done a little bit of this a little while back, but we can always go from grams of a substance to moles of that same substance using the periodic table. So I can go to moles of oxygen using the periodic table, because if I go to the periodic table, I know that 1 mole of oxygen weighs 16 times 2, or 32 grams. Okay, so that'll get rid of grams of oxygen. And then from moles of oxygen, this is just like what I just did, right? So this is a mole-to-mole step. I can go directly from moles of oxygen to moles of water. That's exactly what I just did. It's a 2-to-1 ratio. So the only difference in this problem compared to the previous one is this first step where I used the periodic table to go from grams of my substance to moles of it. So now I'm just going to go 45 times 2 divided by 32. So that gives me 2.8125. Or with sig figs, based on my starting number, which has 3, 2.81, and my unit would be moles of H2O. And so that's basically stoichiometry. The only thing that we need to add at this point in terms of a further step would be going from grams to grams. So I'm using the same starting number, 45 grams of oxygen, but this time I'm going all the way to grams of water. Now I could just start with 2.81 moles of water, because I found that based on 45 grams of oxygen. So I really could just take one more step and go to grams of water, because right now I have moles of water. But just to give you an example of a problem that goes all the way from grams to grams, I do want to show my work for this whole problem, this time at least. So 45.0 grams of oxygen. And by the way, if you think you have the hang of this at this point, or are starting to get it, obviously at any point, pause the video, use your scratch paper, see if you've got it. You don't have to wait for me to work it out. But anyway, if I'm going from grams of oxygen, ultimately I want grams of water, but first I have to go to moles of oxygen. Again, using the periodic table, so 1 mole is 32 grams. And then from moles of oxygen, just like the last step, or the last problem, I have to go to moles of water. And going all the way back to my balanced equation, that was 2-to-1, right? 2 moles of water for every 1 mole of oxygen. And then from moles of water, we would then go to grams of water. Now it's a molecule this time, but that doesn't really make much difference. That just means we have to add up a couple of different molar masses from the periodic table. So 1 mole of H2O should come out to about 18 or 18.02 grams. And I'll go ahead and do that math. And that's going to give me 50.68, or rounded to 3 sig figs, 50.7 grams of H2O. So what we've done so far is we've gone from moles of a substance to moles of a different substance. That's our simplest type of conversion. We can also go from moles of substance A all the way to grams of that second substance. We'll just call it, substance B. And we can also go all the way, starting from grams of A, we can go all the way to grams of B. It just becomes, 1, 2, 3 steps, if that's what we're doing. Okay, for this last part, I'm going to put some practice problems up there, get out some scratch paper and a calculator and a periodic table, and see if you can answer these questions. So first of all, balance the equation. Okay, so you should have come up with a 2 in front of NH3 and a 3 in front of H2, and that does it. All right, so let's answer the first question. How many moles of hydrogen are needed to react with 14.8 moles of nitrogen? Okay, you should already know whether you got this right or wrong because you answered the question, but it's just basically 14.8 times 3 because there are 3 moles of hydrogen for every 1 mole of nitrogen. So I get 44.4. So let's try the next one. How many moles of nitrogen are needed to react with 55.2 grams of hydrogen? Okay, and there you have it. We had to use the periodic table to go from grams of hydrogen to moles of hydrogen, and then use the balanced equation to go from moles of hydrogen to moles of nitrogen. So let's try the very last one. How many grams of hydrogen needed to produce 62 grams of ammonia? Okay, and there you have it. It was grams to moles using the periodic table, and then moles to moles using the balanced equation, and then moles to grams, again using the periodic table. I get 11 grams of hydrogen. So make sure you come to class ready to go doing some more calculations and with plenty of questions if you have them.